Good morning, happy Thursday, everybody. Welcome back to another wonderful day of Algebra 1. Hope you guys are having a great day so far before you're watching this. Couple quick announcements before we jump into today's lesson. First and foremost, we had a quiz yesterday, formative quiz number 9, so please make sure that you watch or take that quiz before you close your Chromebook for today if you have not already. Speaking of turning things in, we have homework collection number 11 should be open and is ready to be turned in today. So please make sure you get that taken care of again before you check out for the weekend. One last note, if you are a virtual student, a lot of this chapter, about a third of it, is going to be taking place on Mondays, so when you're not in live class. So make sure you are paying attention, doing those lessons on your own, watching those videos we're putting out for you guys for Mondays. It'll really help you as we go through this chapter and help you keep caught up. So other than that, a couple other notes we'll get to in a little bit, talking about the homework more specifically, but I'll flash the answers up from Tuesday's homework very quickly. Again, if you want to check these out in a little more detail, feel free to pause the video, check these out, or check those filled in notes. And there we go, moving on. So again, we should have our white packets open to 7.1.2. We're talking more about exponential functions today, how they work, what they might be similar to in the past from what we've seen. So we're going to go a little bit out of order today. And in fact, instead of starting with 720, like we can see on the left-hand side of our page, we're actually going to start with 721. So if you want to turn to the next page, we're going to look for this part right here. Dealing with exponential functions, again, they have the form always of y equals a times b to the x. So when we were in class on Tuesday, we talked about functions that were of the form y equals b to the x, where we changed our multiplier b, or kind of saw what happened when we changed that number around, whether it was 0, whether it was 1, whether it was greater than 1, or between 0 and 1. But we assumed that that a value out in front was a 1. So we assume that a was equal to 1, but that's not always going to be the case. So as we can see on the right here, we've got y equals 2 times 2 to the x power. So what does that kind of look like? So if we follow the shape of that graph, again, that kind of looks like something we might have saw in chapter 5, like one of our geometric sequences, where we start really, really small to the left, and then as we go to the right, those y values get bigger and bigger and bigger. It looks like we're kind of doubling those values again because of our multiplier right there. So when we talked about arithmetic sequences way back at the start of chapter 5, arithmetic sequences and linear equations were very much the same, except for we just basically changed the letters. And that's kind of how exponential functions and geometric functions, or geometric sequences, work as well. Where when we had our geometric sequence, t of n, that was t of n is equal to our initial value t0 times our multiplier raised to the n power. Where if we look at this formula up on top here, y equals a times b to the x, those two things are basically exactly the same. Again, we're just changing those letters around. So y is equal to a times b to the x. The big difference, again, is when we have y and x's, we are going to have a continuous function, which is why this graph is entirely filled in from left to right. We don't just have the dots at the whole numbers for x. So what does a represent and what does b represent? So again, when our sequences, we had t sub 0, that t sub 0 was our initial value, or that starting value for that sequence. That is exactly what a is going to tell us. So a is our initial value. Whereas b, again, with our sequences, r was our multiplier. Again, that's what we were experimenting with on Tuesday, so we already know that b is the multiplier for our exponential equation. So this is our multiplier. And then x is just x. That's the number that we're plugging into that function to get that specific output of y for that given equation. So again, a is the initial value for this exponential function. B is our multiplier. Again, very similar to our geometric sequences. So how can we identify this by looking at a table? Well, that's pretty simple. How can we identify a where we're looking at a table? And it's our value when a t is equal to 0 for our sequences. So similarly for our exponential functions, by looking at a table, we can find this where x is equal to 0. Find where x is equal to 0. Otherwise, if we look on a graph, where x is equal to 0 is going to be our y-intercept. So again, on that graph right now, that is at 0, 2. This is a 2 right there, so it makes sense that that would be our y-intercept. Awesome. So if we want to find our multiplier, if we want to take our find our multiplier, there's a couple different ways we can do that. If we're given a table, we can do it the exact same way that we did for our geometric sequences when we were trying to find the rate. We can take any term and divide it by the previous term. And that will help us find b instead of r this time. This will help us find our b value, our multiplier, exactly like our geometric sequences. So if we did that here, let's say, for example, we've got at 2, x is equal to 2, our y value is 4. If we go over to x is equal to 1, y is 2. So if we take 4 divided by 2, we get our multiplier is 2, which is exactly what we've got in our equation. So it does work. Perfect. So that's how our exponential functions work. Let's work through a couple practice problems here and see if we can't nail this down a little bit better. So let's go back to the first page of our lesson and go to 720. So Arnold dropped a ball during the bouncing ball activity and recorded its height in a table. So part of the table is shown at the right. So we want to find a couple things here. First things first, what is the rebound rate of the ball? So the rebound ratio of the ball, or basically what is the multiplier between those two things? At what height did he drop the ball? So that is telling us what's the starting value for our exponential equation. And then lastly, we want to write an equation that represents his data. So we got to find a few things here. Again, knowing that our equation is y equals a times b to the x, we've got to find a, we got to find b, and then we got to plug it into that generic equation. All right, so let's find our b value first. Let's find that rebound ratio. So just like what we just talked about, we can take any term, divide it by the previous term, and we will get the multiplier for this exponential function. So let's use 3 and 2. So if we use 3 and 2 for our bounce number, that means that our b value is going to be equal to 67.6 divided by 84.5. When we evaluate that, we will get 0.8 as our multiplier. And we're just going to leave it as 0.8 because that seems to be the simplest way to do it. We're just going to leave it as 0.8. We could leave it as a fraction, but we're just going to put it as a decimal for right now. So if we remember from our sequences, if we want to go from 2 to 3, we have to multiply by our multiplier, 0.8. If we want to go from 3 to 4, again, we have to multiply by that 0.8 once again. But if we want to go up in our table, we have to do the opposite operation here. So if we want to go from 84 backwards to number 1, or bounce number 1, if we want to go back to our initial height, again, we have to divide by our multiplier instead of multiplying. So it's the same thing with our arithmetic sequences like we talked about before, but now we're just doing it with our multiplier in our exponential function. So if we take 84.5 and then we divide it by 0.8, the height of the first bounce will be 105.6 centimeters. And again, if we divide this number by 0.8 one more time to go up to our initial starting height, we would get 132 centimeters. So that's the two things that we needed to find. We needed to find our initial height, which is right there. We needed to find our multiplier. Now we just got to plug it in to our equation right here, y equals a times b to the x. So our final equation for this one is equal to, y is equal to our initial height, 132 times 0.8, all raised to the x power. Awesome, moving on. Next one, part B. So a major technology company, Expo Grow, is growing incredibly fast. The latest prospectus said so far the number of employees, y, can be found with the equation y equals 3 times 4 to the x power, where x represents the number of years since the company was founded. So find a couple things for me. Pause, try to work this one out on your own, given what we talked about. Find how many people did the company start with, and how can the growth of the company be described. So just answer those two questions for me. Pause the video, and then we'll talk about it here in about 2 seconds. So pause it. Let's keep moving. So how many people started the company? Again, our a value is our initial value in our exponential function. So a equals 3. So that tells us that 3 people founded the company, or there were 3 founders. Next, how can the growth of the company be described? Again, the growth is represented by that multiplier, which is our B value, which is the 4 in this case. So again, with B equals 4, that tells us that the number of employees is multiplied by 4. Each year. There we go. Again, multiplier is greater than 1, so we know that our function is going to be growing like we talked about on Tuesday. So when we have a positive or greater than 1 B value, we're growing. In this case, we're multiplying our number of employees by 4 every year, starting with 3 founders. Moving on. So C, this one is a little trickily worded, so follow along with me on this one. So a computer virus is affecting the technology center in such a way that each day a certain portion of virus-free computers is infected. So the number of virus-free computers is recorded at the right. How many computers are in the technology center? So perfect. How many computers are in the center? Again, that's our initial value at day 0. That's what we're starting with. So we can look at our table, figure that one out right away, and that's going to be 27. 27. First one is pretty good. That one is 27. Next one, what portion of virus-free computers is infected every day? So that's kind of worded kind of weird because we have uninfected computers over here. We're trying to figure out infected computers, but I want to figure this out maybe in a little bit different way. So instead of thinking about how many computers are infected, I'm going to kind of flip that thinking and think how many computers are staying uninfected every single day. So like, well, how many computers are remaining uninfected by this virus as we go from day to day? So again, that's finding the multiplier between 2 of these days. So let's do between day 1 and day 0. So we take any term divided by the previous. So we got to take day 1 divided by day 0. So our multiplier here is going to be 18 over 27, which if we simplify that is going to be 2/3. I'm going to leave this one as a fraction. So that means 2/3 of the computer from the previous day remain uninfected. So we're just kind of flipping that question a little bit. That's kind of weirdly worded, but 2/3 of our computers going day to day remain uninfected. So how many virus-free computers will there be at the end of the 3rd day? So again, what is the next row in this table? It's basically what is that asking? How many computers are going to be uninfected with that computer virus after day 3? So first, we know our A value, we know our B value. Let's 1, write an equation, and 2, we're going to plug in 3 because we want to know the value of the 3rd day. So y is equal to A times B to the x. We know A and B, so let's plug it in. Y is equal to 27 times 2/3 raised to, in this case, we want to find the 3rd day, so x has to be 3. So when we evaluate this, we will get y to equal 8. So on day 3, there will be 8 computers remaining that are uninfected with that computer virus. Awesome. Last one here. So part D, we're looking back at that same exact company from part B. Apparently they had a major scandal, and it was discovered that several statements in their report were false. So if the company actually had 5 founders and doubles in size each year, what should the new equation look like? So again, try this one on your own, pause the video, and I'll go through it. So pause it, and we're gonna go through it. All right, so again, we have 5 founders now, and doubles in the company, doubles in size every single year. So 5 founders means that is our A value because that is what we are starting with. That's its initial value. So this is our A. It doubles in size every year. So that doubles tells us our multiplier. This has got to be B. So our new equation, if we just plug it into, again, this general form right here, y has got to be equal to 5 times 2 to the x power. Awesome. So one last problem for today. We're going to go to the next page on the bottom underneath 21, like where we did before. We're going to go down to the bottom of the page and do 23. We're going to talk about how to sketch these very roughly how to sketch these graphs very roughly as we start talking about these exponential functions more and more. So we want to graph the function y equals 7 times 2 to the x power. So again, think about what those numbers mean. So if we think about y equals a times b to the x, put that in parentheses, a times b to the x, where again that a is our initial value. Initial value, or if we think about initial value in terms of a graph, that is our y-intercept. So if we know that initial value is 7, that's our y-intercept. We can start by plotting that point first. If we go over to our graph here, 1, 2, 3, 4, 5, 6, 7 spots up, that's where we can start our graph. Because that a value shifts our multiplier. Because if we raise 2 to the 0 power, that's 1. 1 times 7 is 7. So that shifts that intercept up for our exponential functions. So for our multiplier now, we know as we go to the right, because 2 is greater than 1, we're going to be increasing as we go to the right. As we go to the left, we're going to be decreasing again because that b value is greater than 1, and it has to fit the shape of that general graph that we talked about on Tuesday. So as we go to the right, we have to double this 7 every single time or double the previous value every time we go to the right. So when we plug in 1, we have y equals 7 times 2 to the 1. Anything to the first power is itself, so this one is just going to be 14 for y when x is equal 1. So if we have to go over 1, we can add 7 more. 1, 2, 3, 4, 5, 6, 7. Close enough. And then if we go backwards, we're basically doing the opposite. We're dividing that previous, or the one before it, in half. So if we go backwards, we got to cut 7 in half to get like about 3.5, which would put us here. And if we keep cutting those values in half as we go to the left, we'll get the rough shape for this graph, which should look something like that. So when we can now connect the dots, it should look something like that, even though that was not great at connecting the dots. But the big point, the big spot that we should know how to do, especially when we're graphing these, is knowing that that front number, that a value, is again our y-intercept. If we can graph that spot for sure, just by looking at an equation, we should be able to get the rough shape of that graph given our b value from there. So that is where we're going to stop in the notes for today. We do have a couple things to add to our toolkit, so if you want to grab those out real quick, we have a couple things to add in case you have not yet. So we talked a lot about exponential functions the last couple of days. We want to make sure we get those notes onto our toolkit. So first and foremost, the general form for an exponential function, like we talked about today, is a times b to the x. A times b to the x power. So again, a is the initial value. And on a graph, that is our y-intercept. And b is the multiplier, where b is always greater than 0. Can't be negative like we talked about on Tuesday, because then we get that weird oscillating function going up and down and up and down. So b has to be greater than 0. If it's 1, it's just a horizontal line, but we'll kind of keep that off the toolkit just for the lack of space. But that's what we got. So a is initial value, b is the multiplier, b is always greater than 0. When we think about increasing exponential functions, b is always, always, always greater than 1. B is always greater than 1 for our increasing exponential functions. And what that graph looks like, again, we're starting really small on the left, going through our intercepts, and then getting really steep as we go to the right. We are continuous in both directions. For example, the b value could look something like b is equal to 2, maybe 4, maybe 8, something along those lines. So decreasing exponential functions. In this case, b is between 0 and 1. Like if we had like a half, a third, or a decimal, something along the lines of like 0.8, like we saw in our lesson today, or 0.76 or something along those lines, that would be an example of a decreasing exponential b value. So again, what that graph looks like, we're really steep on the left, then we're working our way smaller as we go to the right. We get closer and closer and closer and closer to that x-axis, or y is equal to 0. Which there was a fancy name for that, like we talked about on Tuesday, and we're going to, again, add that onto our toolkit as well, where we have an asymptote. An asymptote is the distance between the graph, and an asymptote gets closer and closer to 0 as that line gets closer to it. So when we have our exponential functions, that asymptote is 0, because we're going to get closer and closer to 0 but never actually touch it. So if I just draw the new one so we can kind of see it a little bit better, I'm going to put our asymptote at y equals 2 instead. So y equals 2 is our new asymptote. Y equals 2 is that new asymptote, so we're just going to draw another random exponential function that's raised up. And there we go. So that's what that asymptote looks like. Again, we're getting closer and closer to that asymptote as we go to the right. My lights just shut off on me. But that is not important because we are done. That's all we got for the toolkit for today. So next thing and last thing is the homework for tonight. 724 through 728, 7.1.2. Again, do not do number 29. We don't know how to do that. So make sure, again, you get your formative quiz taken care of. Turn in that homework collection from this week. If you have any questions, reach out to your grading teacher. Otherwise, have a great weekend, folks, and we'll see you next week.